Okay, so yeah, maybe we can start. So now we have this talk by Jeff, and he will tell us essentially about his views on machine learning and how to use it or not in physics. Okay.
Thank you, Andrea. Yeah, so my background is I've been using machine learning for about 15 years on many different types of problems. Actually, many problems out of physics. But I'm a theoretical physicist by training, quantum field theory, mainly in condensed matter physics. So it's very interesting to watch this area I've dealt with for quite a while coming into physics and seeing the reactions of physicists to it who are maybe seeing it for the first time, especially younger people who maybe don't even know much of the history of where machine learning came from. And so I thought it would be more fun, since this is not the conference, this is more casual now in this sort of workshop portion of things, to have this kind of talk where we kind of think about what is machine learning and when should you be using it, or what should you be expecting it from it. So this is a kind of a perspective, and in some ways it should, if you're very excited about machine learning, it should irritate you a little. Okay, it should make you a little concerned about machine learning a little bit more, okay, and be a little bit more careful. I mean, I think enthusiasm is good because it makes you motivated to do interesting things, but there's also an element of caution we should have in using these tools, because I've seen them do spectacular failures, and I'm not sure physicists fully know about all the spectacular failures that have occurred, because people don't write papers about them. They just quietly shovel them off to the side. But if your machine learning thing works, then you write a great paper to go to NeurIPS or ICML, and everyone is talking about what a wonderful paper it was. So this is a little bit of the cautions of what happens behind the scenes is a lot of this stuff. But as I pose it here as a Faustian bargain, we obviously have to have the seduction phase, right? Where we want to have the machine learning. And it's certainly, there are many amazing things about machine learning. And so I went to my account on OpenAI and used this tool that you may have, it's gotten quite a bit of press lately, called DALL-E 2 at OpenAI. This is Elon Musk's version of machine learning. And it's very interesting. You can just type in a string into this, and then it goes off into the cloud computing for a little while. And just from this string right here, it will create an image never seen before, assembled together from the phrasing that you typed into it right here. So I thought yesterday, as I was preparing some of these slides, it would be fun to type this in, physicists talking about machine learning in Florence, Italy, and see what the machine tells us it is. So here's a couple of the images it created. Okay, I don't know if that, it's sort of it's interesting, the nature of bias, how machine learning finds bias and things. But you know, there's your typical physicist, I guess. So if you don't look like any of these people here, maybe there's a problem, right? But that's the funny thing. This is just showing you aggregation over the data, and then when you assemble these images. So these are just images it put together. So I guess you're kind of also seeing, what is Florence? What is it like to be in Florence? It's to have these buildings and have, you know, you're down at the Uffizi talking about machine learning or something. And I thought, well, that's kind of, it's interesting, right? It's kind of interesting it does this. So I thought, well, you know, let's do something even different. Let's make an impressionist painting of us talking about machine learning and see what this amazing resource comes up with. And so this is the impressionist painting of us talking about these things. And, you know, I was kind of surprised, because it's like, I actually kind of like these. So the machine does pretty good. In fact, this is creating a lot of irritation amongst artists, because there is a output of this program was submitted into an international art competition and won. And so to artists that AI replacement line is coming close, right? And I think it's kind of fascinating to watch as disciplines come up against the capabilities of AI. And this is pretty good. I'm not really sure what's in that painting there, and I'm not sure what the machine thought machine learning meant in the painting. But, and then just one last one before I move on, I thought, well, it's called DALL-E, so let's make a DALL-E-esque version of machine learning, people discussing it at least over pasta or something. That seemed very DALL-E-like. And so I don't know, I guess you would look at that, if you saw that, you said, you think DALL-E would have created something like that? Maybe. It's got the style of it, right? So I would say this is rather seductive, isn't it? This is a tool. I mean, think of this. This is actually, in some ways, as complicated as a physical model, to have a generative model based upon all these images and being able to composite it and assemble it together and present it to you. And you go, well, you know, it actually captured some of the essence of what was going on there. That's a lot of power. It's tantalizing. So, you know, you might say, well, how does something like that work? And then the machine learning people say this. And you have some crazy solutions that they've tacked together, and you discover that it's this wild activity going on that's been hacked together and over many years at times. And so there isn't really an answer. It's like you no more have an answer of how you walked in and sat down in this room than what you can get out of some of these explanations. It's like, this is your brain doing stuff. And it is kind of a hack that's very hard to make formal. Now, of course, their real image is this from the paper. But I would argue, I'm not sure exactly how much one can get out of it. I look through the paper and it's really acronyms and sort of complicated references back to other things. And so it's not easy to understand how you do this, other than, well, they concatenate some vectors and they have text tokens and they have image tokens, and they're sort of aligning them in some semantic space. Okay, so there's kind of those boxes with that neck down that encode and they neck out and they decode, and the usual architecture of describing these things. So the Faustian bargain here is the devil is telling us you can have all this power, but you may not be able to understand what it does. And it reminded me of a phrase that's pretty famous in mathematics about geometry and algebra. So this is Michael Atiyeh, is like the Singer-Atiyeh index theorems in differential geometry. So he's a very famous differential geometer. And he was sort of saying this, like, this is like a Faustian bargain the mathematicians had about, you can have the machinery of algebra, but you get the geometry taken away from you. And that happens a lot. Remember, you take your classes and you work in physics, and sometimes it's just doing the algebra and you don't know what the hell happened. Something results from it all. And you say, well, I guess that's the answer, you know, because I turned the crank until I got to the end. But you don't really feel like you really understood it, or at least for me in physics, till you had a sort of a geometric sense about what was going on. And so that's kind of my theme here, is that when you use machine learning and you sort of are in this algebraic mindset, algebra and machine learning are very closely connected in these kinds of formal manipulations. Whereas, you know, I want the curve, I don't mind having the geometric definition of the curve, where it's a locus of points that obey equation. That's fine. But I would also like to have somewhere in my mind the curve over here, the notion of the curve as this object. And so I want to try to go through here with the time we have and maybe sensitize you to the fact you should want to do this too, that you should want to think about the geometry of these algorithms, because geometry is very important to physics. It makes, in many ways, understanding the geometry that the physics takes place in has led to the incredible advances in the past, you know, 100+ years of physics. So if you're going into machine learning, don't try to become like the computer scientist. Stay a physicist. And you may have to adapt these machine learning tools. I know it's great to go to GitHub and just suck down some Python toolbox and chain the toolboxes together. I deal with students at Padua, and they just, it's amazing to me, like they perform these acts of like, who knew you could say, I'm going to invert 100 million element Jacobian, you know, with automatic differentiation. And for my age, it's like, wow, that's incredible. But why are we doing it? You know, what's the purpose of that object? And what does it mean when we've done it? And, you know, these are things we should still think about as physicists. So I hope you understand the nature of this Faustian bargain. And it's important, I think, to sort of understand that machine learning is a sort of a transactional area where it's not that you understand it, it just works. That's what most people say. When I pin them down about an algorithm they're working on, it just works. In the end, that's what they go to. So it's really about that performance. And you like the performance, and people want that. And I can appreciate that. You want some kind of performance out of that algorithm. But in physics, you know, we have some. All right. Okay. If I'm talking about something complicated, I should be able to work a laser. So in, you know, machine learning is like the revolt of the computer scientists who got sick of listening to the statisticians. And so what they did was they said, well, we're not going to listen to them anymore. And we're going to just make up stuff because we have lots of data on computers and we would like to understand it. And the statisticians keep talking about, you know, Fisher irises and, you know, these weird, very low dimensional data sets that don't seem to matter. So they went off and they did a particular style of statistics called what we would call exploratory data analysis. Now, of course, what they ended up doing was they reinvented statistics. Because, you know, it's not like, well, there would be a totally other kind of statistics, but they reinvented it, but in some very interesting ways. So I kind of think of as machine learning as sort of the more sexy, interesting version of statistics. Okay. And mainly what it does is it deals with high dimensions. Right. And the statisticians were very fearful of having problems that were in very high dimensions. But the machine learning people didn't care. They're like, no, I'll think of my image as a 1 million element vector. And let's see what happens. Let's figure out how to do the algorithm. Now, the things that you lose, though, since you're focusing on just prediction, is that here in physics, natural sciences, we've also never really liked statistics. Right. There's this phrase I saw Marco Zanetti had in his talk. It was like, I've had it in my talks for years too, about when Rutherford said, if you need statistics, you should have done a better experiment. And so the physicist's level of sophistication, this is, of course, the character, is that, you know, they will take the logarithms of their axes to find that straight line. And, you know, that's sort of a physicist's data analysis. And if you can analyze your experiment with just doing that, everyone feels like this is very good. This is a trustworthy experiment. But as things get complicated, like some of the problems people have talked about, whether they're cosmological astrophysical problems or whether they're problems in high energy physics, you're not just going to take the log of the axes and figure out the problem, right? It's much more serious, and something like machine learning is important. But you do want to have some sense of just causation, not just maybe correlation and association. I know physicists actually strangely don't think about causation much because it's like so built into so many of the theories that it's invisible. It's like the fish has no word for water. And so causality is kind of in the mix a lot of times, but it's not formally defined. So most physicists would be hard pressed to say, I give you some data, prove the causal relationships within it. And to a physicist, that's just like, what? How would you do that? Well, there's a whole field that works on that problem. And it had to come from places with awful data like sociology and psychology. The worse the data is, the better the algorithms are, because they have to fight and fight and fight to figure something out. And physics has these amazing experimental physicists that serve up this golden platter of data that's just astonishingly good. And you're not pressed to do the kind of data analysis they are in fields like economics or psychology. Okay, so a lot of the machine learning things that you may know about actually came from those fields, and machine learning sort of pulled them in. And actually physicists over the decades have gone into machine learning and created a lot of the algorithms. It used to be the Ising model was used for image segmentation, things like that. Statistical models were brought into machine learning. And it was really funny watching the machine learning people try to explain the Ising model. So it's a the transfer goes back and forth between the fields. So the point is, though, if I can use this laser again. Here we go. Maybe we can't have all the parametric models that physicists like to have, and we may want to have some machine learning. And so the trick is, how do we try to retain some interpretability, explanation, understanding, and not just give in to the Faustian bargain down here of saying, I'll give you all this great prediction, but you won't understand anything that's going on. And it may not work all the time. Like, that's machine learning. It's like a lot of the things, they work, and then they don't. And then you don't know why. And then you're struggling to understand, well, what's different now about my data, and why is this not converging? Why is this not working? And so we want to try to get into the sector up here, I think, where physicists learn to tolerate non-parametric models versus parametric. And by that, I just mean, it's not that there's no parameters, it just means there's a lot of them. It means there's could be an infinite number of parameters, and that's very not comforting to a physicist to imagine that. But there are ways to control that problem like they do in machine learning, but then still try to have this explanation and even causation still being in the mix. And I think this is the terrain we would like to go to, but machine learning doesn't really quite get there. Okay, so that's, if you just want to stop listening at that point, that's sort of the key message I would say. So this part, right? We mainly have two types. There's many types of machine learning, but mostly I think you guys I saw some people talk a little bit about reinforcement learning, but mainly it's supervised or unsupervised learning that you're doing. And the statisticians always get rankled because they say, well, that's just density estimation and that's just regression, right? And they're right. These are just more fun names for it, with the word learning in them. And so you have all the types, classifiers are just sort of digitized regression, right? And then you can have the intermediate case between regression and classification, where you just have sort of binning and quantization. So there's nothing fancy about that. And then unsupervised learning says, I'm not doing regression where I have two spaces I'm trying to build a map between, but I'm actually in one space and I'm just trying to understand how the data is created in that space, right? Just like you making a PDF. So that's pretty straightforward. So the challenge, though, is in supervised learning, you're controlling everything you do with some kind of label or something that you're saying, I want to preserve this quantity as I pass it through some huge space potentially. And maybe I don't even want to build a probability model in here. I just want to be good at making sure when I pass my label through this crazy space here, that it comes back out the other side. Right, that I can do a mapping through this high dimensional space, and I may want to send my data to some feature space where whatever geometry, and every machine learning algorithm has an implicit geometry. It's when someone says this algorithm has blah 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 inductive bias, generally they mean it uses these geometric structures in it to make its solution. Okay, so it's always good to know when somebody's talking about, this type of neural network or support vector machine, well, what kind of object is it being built up from? What are the components of that? And so they all happen in here, but you try to preserve this labeling across here. So this is kind of the same thing, but with more of the information theoretic viewpoint to it, is that you're saying, I have data and I have something I care about in the data. I don't care about everything in the data, right? And you'd say, well, it just means I have a particular thing I'm trying to do with my data. And I may be a simulation and you're like, oh, I need to coarse grain it. I need to bin it. I need to reduce the scale of this data to make it more manageable, or build an emulator. Well, I want to build an emulator that doesn't emulate all this stuff that I don't care about. And so you say, well, I have to send it through this bottleneck. And the bottleneck is like a probabilistic graphical model where you say, well, I take my data and I compress it. And then this is the compression. This is the mutual information. I'm not going to go into a whole, if you don't know what mutual information is, just think of it as like it's the bits shared between two random strings or signals, okay, for our purposes right here. It has a much more formal definition related to the entropy between the joint probability and its marginals, but we can not, I'm not teaching it here, so let's don't get into that. But the point is there's a formal way to understand this compression, and you can sort of set a Lagrange multiplier to say how much compression you actually want. So this is a very interesting approach to thinking about these. And by the way, a physicist helped create this some years ago, Bill Bialik, who was at Berkeley and then is at Princeton now in the physics department, helped create this idea along with a computer scientist, Natafli Tishby at Hebrew University, I think. And this is a fascinating way to look at what you do when you're creating a model and understanding how you compress it. So this is sort of supervised learning thought about very carefully as model compression. Now, the trouble with supervised learning is, and I'm not sure physicists fully appreciate this, is that supervised learning is the devil. That is the most dangerous thing to play around with, because you think you know what it's doing, but it's doing something else. In my experience, it is one of the trickiest objects, because you don't, it's like, what did Feynman say? It's easy to get fooled and you're the easiest one to fool. And you will fool yourself with what you think one of these algorithms is doing, because labels, if you think like I was like the Galaxy Zoo problem, or what, other problems where you'd say, oh, well, I know what I want to have in my data, I know what matters. That may not be what the algorithm thinks matters or does, and it will trick you, and it will find funny ways to solve the problem, and you're like, it looked like it did it, if you only look at performance. But you have to remember the labeling and what goes on in the world is very, very complicated. It's almost like this is a reinforcement learning problem. And then at the end, you sort of scrape off that top layer, like the language level or the high level perceptions of your brain. And you say, somehow I'm going to take these and I'm going to take them over into this other problem and drop them in as a part of this regression over here to do the supervised learning. So here's the supervised learning, but the relationships of the labeling and the concepts and all that stuff actually depends on this massive structure that took place over evolutionary time to create your brain and the words and the language and what you can pick out. And you have to be aware that you're now trying to steer a potentially very high dimensional signal with a very, very low dimensional signal, which is the labeling structure. Okay, if I'm saying I labeled a cat and a dog, and the cat and dog vectors sit in a space that's a million dimensional, but I have a 2-bit guiding, measure, you use some very strange things can happen. Okay, and so I would say be very cautious of supervised learning. It is the place where it's like card tricks. It's like a magician shows up and does a card trick for you, and you're like, that's amazing. Look at that. The machine's thinking. It can recognize the cat and the dog somehow. Have more skepticism. It is a bit of a trick when you do this and just sort of pull these labels over here. I was fooled when I started out doing this, and it creates terrible problems. So hopefully that's enough of a warning. So now I'm going to go and beat up on neural networks for a little bit. So this is the little short history of machine learning. And I thought maybe you've never seen something like this before, but so you might like to. So neural networks, which are, of course, a very powerful approach right now, all right? Well, they've actually died 2 times before. This is the 3rd time they're back, okay? They've risen from the dead for the 3rd time, all right? And the first time they died was back here in the battle in what they called the connectionists versus the GoFi people. The GoFi is for good old-fashioned AI. It was really symbolic computing developed by the groups at Dartmouth at the very early days in the late 50s and early 60s, where they built theorem-proving machines in the 60s for math theorems. And so what happened though was they realized they couldn't solve this very simple problem that Marvin Minsky posed in his book Perceptrons. And basically this book, Minsky is a famous computer science, cognitive science professor at MIT. And he wrote this book, and it basically sort of destroyed neural networks because they couldn't solve like this simple problem called this XOR problem, which is just finding the boundary of a single layer perceptron to separate the data. Now, obviously, you can add layers to the neural network, and this will be better and more interesting, right, if you can do that, but they couldn't train it. They didn't have back propagation yet. So neural networks died here, maybe unfairly. There was like politics involved too. The people went behind their backs and cut their funding inside the US government to kill these programs. Yes, sir.
Sorry, just a curiosity, like a historical curiosity, because I mean, as far as I know, like you can solve the XOR problem with a neural network with like 4 neurons. So, like, I mean, this must be trainable because it's something that you can solve like by hand. So why did they simply?
Well, they were just having, I guess, this perceptron was just this hyperplane. It was kind of like a support vector machine.
Yeah. But,
and they sort of posed it this way. I know. I mean, I'm sympathetic to what you're asking. I don't exactly know the history of why the problem was so hard,
okay.
but you know, they're sort of sitting there going, well, if I do this XOR problem right here, I can't really draw one plane that separates the green and the red. And you know, we would know now. We'd say, well, just put it into, you know, if you add a third dimension, it's not a problem. I know. Everything seems easy to us now because we're looking back at it, but this was like a deal killer for the single layer perceptron.
Politics is politics.
Yeah, and there was a lot of politics because the symbolic people wanted to kill the connectionist stuff. They didn't like what the connectionists were doing. So anyway, they died. The neural networks died the first time here with Minsky, and then there was sort of a resurgence when people figured out that, you know, this is funny. It's like Jeff Hinton, who's very famous, you know, for learning. He likes to say at conferences like, then computer scientists learned the chain rule from calculus. And that's back propagation. And so they learn back propagation, and suddenly you're able to do multi-layer neural networks. And so there's a resurgence again in the 80s here where you start seeing, and this is actually when like LeCun was working, you know, like LeCunNet. That's when convolutional neural networks were first created in 1989 with LeCun at NYU. And so that was like, oh, a renaissance, right? This is happening. But then the thing that killed neural networks that time was statistical learning theory. So I guess coming out of the Soviet Union, Vladimir Vapnik, who was very famous because he was the creator. He actually did theory and created an object that was useful from it. And that was the support vector machine. So he's the guy who figured out how you do a support vector machine. And then kernelization with support vector machines just took off in the 90s, mid 90s, through this region here, through the whole 90s and up into the to the 2000s here. And that was sort of like, oh, that's the way forward. We're going to do statistical learning theory, and we're going to have kernels to, you know, map us into the interesting spaces and things like that. And that killed the neural networks for the second time. And then Hinton, who always loved neural networks, and his students, they're like, we're going to fight our way back into this. And they finally did. And they got enough, you know, GPUs were starting to be developed. There was better computational platforms. The internet had come into existence. And so a lot of it was the same algorithms, backprop and CNNs that existed back here in the second renaissance of neural networks. All it needed was basically more power. It needed more computational power, and it needed better data sets. And so once you had the data sets come in, you know, to train on, and you had the computational power to do that and figure out how to make sure backprop could push that signal deeper through many more levels of a network, you had the deep learning stuff taking off. And that's kind of this red line right here. And so all of a sudden, all these tools, you know, boosting in force, although I'll say the deep learning people love to go on about how they're so amazing, but when you actually look at competitions like Kaggle and things, these boosting and the trees and boosting right here, which are extremely powerful. You know, if you don't know what they are, they're well worth understanding and knowing about. Random forest and boosting algorithms. They're the ones that actually can beat deep learning. And so, in many supervised learning tasks. So like XGBoost is very famous because it can beat deep learning systems. Absolutely. Now, that's not something people want to talk about at conferences. It's not as exciting, but it's just a fact. So we're here. We're, you know, and I sort of started playing with them at this point right here. And you're kind of living in this dawn of the third era of the neural networks. You know, that's where you've arrived on the scene, unless you've also been doing this a long time. And so the atmosphere is, there's the triumphalism of the neural networks because they feel they've been beaten up so much that they're finally getting their day. So what is, you know what a neural network is, right? It's this, right? So it's this funny way of introducing a nonlinearity, highly coordinate dependent. Okay, so if you're a physicist and you have this, you were taught something about symmetry and you're taught something about, you know, well, you should have equivariance in your coordinate systems. You can throw that away when you play with your neural network. Because it goes and does this funny sigma dot thing and says, here's some affine object, which you'd say, I like that. That looks good. Nice affine object. I'm going to do this mapping, the affine part, the B, the shift. That's fine. That looks good. But now I'm going to decide that the coordinate system it sits in is magical. It's a great coordinate. It's the coordinate system. And I'm going to take this sigma dot and pick off the ith component of that piece of the representation and only pass that through the nonlinear transformation and then give it to you back in the next space system. Okay, as a physicist, I hope you feel uncomfortable. But that is a weird way to do nonlinear transformation. That might not be the way we would want to do them. Okay. The story, though, is if you assemble enough of them together in some special way, it doesn't matter. Okay, but this is the geometry of the object. It's basically saying, yes, do a linear transformation, but it's almost like it's going to use, and I'll come to discuss this in just a moment, it's going to essentially be like a hyperplane boundary set up in the particular choice of coordinate system there, particular coordinates, and you're saying, well, I get this nonlinear change along that perpendicular of this hyperplane, okay? And that is going to lead to all sorts of trouble, and we're going to come to that in a second. This is the main reason why I don't like neural networks. Now, the story is that there's a cost function, like you design your network, and it has some inductive bias, and then you can design some cost function to control what this thing does, and you could input things you understand into this cost function, and then you do this gradient descent, and since it becomes such a big problem, you can't do one big gradient descent, you do mini batches or one direction at a time or one sample at a time, and you do this stochastic gradient descent, right? That's what's going on. And then there's all sorts of things that you use and, you know, that have names like atom and stuff to have sort of like, how do you do that gradient descent in just the right way and descend down and find this optimum right here. And then you find it, and then you've done your fit, right? You fit this neural network to your problem. Unfortunately, this isn't what happens. And it happens maybe in tiny neural networks, you know, this fable is okay. But when you go and do deep learning, or you run something with 100 layers or something, this is not what happens, okay? This thing does this problem is an illusion of an optimization problem. This cost function is merely a suggestion to the system of something you might do, all right? What really happens is it goes into a crazy limit cycle around a high degeneracy of these points here. There's not just one of these. It's actually become a feature that they're scattered throughout this high dimensional space because you can have more parameters than you actually have data. So it's like the whole system memorizes your data, and then it tries to forget the pieces that don't seem to matter. right? So it does this kind of double operation on things. The first one's fast. It happens within 100 epochs of what you're doing. And then there's this very, very, very long part where it has to sit there and prune that memorization step. And they've shown that if you mess the data up in those first 100 epochs of a deep learning system, it never recovers. It's almost like a child that never could see doesn't learn to see if you sort of gave them vision later in life. It's sort of this memorization state really important to these deep learning systems. And it just isn't this simple picture that you get from the very shallow neural networks of doing an optimization problem. So this is the warning for physicists, because there's things called physics-inspired neural networks. You know, I've come to abhor anything that has the word fire in it. It's like it's sort of like a trick. It's like saying it's kind of like it, sort of, but we don't know how. And so what happens is the cost function right here becomes like, well, this is where you're going to put your physics in, right? Your physics is going to somehow live in here. And maybe you somehow put the inductive bias into the actual network architecture of your physics somehow. It's tricky to think about doing that because of this terrible way the mapping works of like picking the coordinate system and only applying nonlinearities along a set coordinate system. And it makes it very confusing how your information comes into the problem, you know, your background information. But don't be fooled that you can just like play with this cost function here and somehow guide your problem here as if it were doing this just optimization to the bottom of the well here. This thing is going into a very high dimensional limit cycle around something. Maybe one of these optimization points, but it's a lot more complicated. It's like a dynamical system, a very high dimensional dynamical system that merely kind of thinks about your problem on the way to doing whatever it does. And the optimization isn't just the cost function that you're doing, but there's regularization sort of hiding both in path propagation and the geometry of the network. It's really hard to figure out what parts are interacting to do the problem, okay? It's a very tricky problem. So people just study the network just as a dynamical object, just to try to understand what it does.
Jeff, as a general comment, I would say that physicists are pretty good in understanding or implementing things like equivariance, which is something we are used to, which you can, built in your model, as well as, well, the choice of coordinates. I mean, if you want to fit some data, like you want to fit a decision boundary with some trigonometric function, you always have to ask a function of what. So that's something I guess we do understand, at least the need for. What at least me, I don't understand at all, is like the second part, how the optimization work and what the optimization is doing. Yeah. So somehow I would say that the place where we are more behind is in the middle.
This piece right here?
Yeah, maybe me.
Well, it would be nice if it just did what was on the advertising brochure, you know, it was like, yeah, if it just did the optimization problem, we'd all be like, well, at least it's just an optimization problem. We can not worry about it, but it's not, it's something else. Yes, please.
What something else? Why is it not going to a minimum?
Right. What I don't understand the question.
My question is, why is it not doing that? Why is it not going to a minimum, but has much more complex behavior? I mean, I would understand it there. So
I mean, think of it. I mean, I don't have a great answer because I think whatever the answer is very complicated. But imagine maybe it would go to the minimum if I could do the full gradient all at once, for instance. But remember, you can never evaluate the full gradient all at one time. So it's almost as if, this is sort of maybe some physics intuition, like statistical mechanics, that if I'm not doing a full gradient computation, which you can't do, right? It's too hard to actually pull that off, and you're doing stochastic gradient, it's almost as if like there's a temperature. There's like you can't get to the bottom of the well because that would be like a zero temperature, right? And so there's always the sense like you can't see all the data and understand the right direction to always go in, and you're constantly being knocked around by the evaluations of the stochastic gradient descent, and you're not able to actually get to the bottom of the well, but you can get in some kind of part of phase space of it to be perhaps around that, you know, on a limit cycle of some kind.
So the main problem are mini batches?
Well, yeah, okay. So mini batches, it's kind of like saying the bigger my mini batch, the lower the temperature, right? And so the ultimate mini batch is the maxi batch where you've done the whole thing. And then you'd say, well, then I actually am sitting in the space and I'm descending. But this is not the worst of it. It's that there isn't even really one of these. So people have shown that there's hundreds of these minima that are almost degenerate. So it's almost like you're doing this in a glassy statistical mechanics problem. And so you're like, well, I'm going to find a minimum sort of that's like all the others. There's like a lot of degeneracy. So the argument is that this is not a bug, it's a feature, because you're always near one of them, maybe, and you sort of descend into that one. And like, well, maybe it's not the global, but the global, the minimum are all about the same. So it's not going to matter if you could say it's the global or not. Now, these are the heuristic arguments you hear, and actually physicists come into these problems and try to say, wow, this is a cool dynamical system to think about and try to work on. I just want to, you know, if you're not aware of it, sensitize you to that this is an interesting problem, and it's not your problem, and you probably didn't want it to be interesting, right? You wanted this to be uninteresting because you're on the way to something else, and suddenly something interesting happened under the hood of this thing, and it's like, we didn't need that. We just wanted, if I'm doing my regression, I just want the regression to happen. I don't need fascinating high dimensional dynamics to occur that I don't understand. Okay. So the neural networks, they grew and everyone was very excited because you could stack them now. You could pass the signals through the various layers of the network, and you could actually back propagate the, yes, sir.
Yeah, so just before we move too far. I mean, there's like this vague suspicion that there's something non-trivial that's happening as you traverse that minima with generalization, and that's why anything in the double descent regime is doing anything at all. But it's not a matter of just like getting stuck here and you have to like somehow jump over here. There's typically
you don't need, evidently you don't need to jump because there's a degeneracy. There's a lot of places you can land, but they seem to be, there's not like a best one, and they're all okay to have descended into. Yeah, but the issue is, I'm just pointing out that if somebody believes that they, you know, you're using an algorithm and you want to understand what are the knobs you can turn to try to control and adjust it. And I'm just saying that, yes, this is a knob, but it's not like it's as direct as you might hope. It's not like in optimization problems where you're like, yeah, I can control my objective function in my optimization, and that is going to, you know, help me in my problem. It's like, no, there's like a lot of, like, for instance, this is what people do, and if you have a different opinion about it, I like to hear it very much. Is that they look at this and they go, fine, we have this, you know, mean squared error type thing. Everyone wants to use that because the derivative of it is now a linear algebra problem. But then they tack on a regularization term, right? So you put on a regularization term and you say, well, see, now this regularization term promotes sparsity, or it promotes something I care about in my problem. It's basically like a log of a Bayesian prior, right, that I'm adding to my problem. And then they imagine that's like, well, now my problem will obey my new rule because I put it in my cost, my objective function right here. And so the good things will happen, right? No, the good things don't necessarily happen because this thing has its own built-in regularization. And it's related to the way backprop works on multiple layers and this weird, like you and I talked about the other day, double descent type behavior. The statisticians, by the way, are going crazy because this is like, they're actually statistics books where they've gone back and I've seen they've had to rewrite things because deep learning is kind of breaking rules of statistics in some way by using wildly over parameterized data sets, yet not overfitting, right? And it's really this idea that there's a hidden regularization going on in the dynamics of this crazy system. And you may go in and say, well, I have my own regularization. I wanted to stick it, go plus, L1 norm of something and add it onto this cost function right here. It's like, yeah, that's there. It's a suggestion. It's a part of what will be thought about in the massive dynamical system as it goes around, but it's not clear it's going to do that much. It's not clear how much it does. Is that fair?
Yeah. So if I paraphrase, is the statement you're making here that there's more to a learning problem than just.
Yeah, but people think that they could do it here, and I'm just warning you that you can't for a deep learning system. Now, if you have a shallow network, that's different. Okay. It's not like it's more like for these big problems that things get really weird, okay, and where you have to be careful. And so, but the trouble is we don't know how that the magic box and whatever it's doing over with the network, the inductive bias by how you constructed the network and how the backprop is working inside of that, it's kind of a more mysterious kind of regularization, right? It emerges from the assemblage of it all. So it's an implicit regularization that sort of is hiding under the hood of the whole object. And then you put an explicit regularization. And I'm just warning you, don't think that's steering the problem as much as you think compared to the implicit regularization that's happening in the problem.
Sure, yeah, I'm happy to agree with that.
Okay. So we stack the networks and then we tell some stories about how each layer of the network represents like interesting features, like here's the edge detectors, like if we're doing computer vision, for instance. So we look at people and then we tell a story about how the input layers figure out edge detectors or Gabor filters like the cognitive scientists like. And then you go to this level and you'll find ears and noses and stuff like that. And then finally, you got the outer layers right before output to, some other discriminative algorithm, maybe not the neural network. This could even be a support vector machine sitting on top of the outputs here. And now it symbols the faces and it's this beautiful sense, like, isn't that how you would have done it? You would have broken the face down, the eyes and ears, and it put it all together. And at the end, it would just make so much sense like this. Well, this doesn't happen. This is not what the network does. Now, you can make a network act this way, but you have to very carefully input a lot of semantic information about ears and noses and stuff like that. So you can make networks behave in this way that we look at and go, how clever these things are. This is a funny story. I think I told it this you, Dave, the other day about there's a well-known computer vision scientist at MIT, Antonio. And I was at this conference. The government had this conference at the National Academy of Science in Washington. So all the deep learning people have come there, and they're all packed in the room. It was fascinating watching them have basically kind of a food fight about all this stuff because there's so many groups that are so irritated learning and the claims, the over claims about it. And then you have the deep learning people are like, look, we're really doing something, which I believe they are. And Antonio Torelbaum was giving, and so I guess you can do this when you're a full professor at MIT. You can stand up there and he said, well, here's this amazing thing and it's on the web and I'll do it right here. And he said, you can open this image up and you can have a palette here and you can say, I want to look at castles and I want to add doors or windows to them. And I go and grab a door off the side palette and I drop it on the image. And then the image is morphed to fit the door in correctly to the architecture of the underlying image. And you're like, wow, that's a pretty good trick, right? And you can go online. I should have put the website here, but you can go online and do this and watch this happen. And he says, that's pretty good, huh? And he said, listen, so this is deep learning at work. Look at this amazing thing. And then he kind of said, yes, but there's a secret to this, and it's not just the deep learning. And he showed a picture of his mom, and his mom evidently loves segmenting images, right? And so 8 to 10 hours a day, she just, I mean, some people do crossword puzzles. Some people want to do computer vision segmentation so their son gets tenure at MIT. Did your mom care that much about your career? You should tell, you can see a higher standard out there. And he said the real trick was that his mom did this, and her consistency made it so that the semantic segmentation was so good they could build a tool like this. So was it the deep learning? Well, certainly that was an important part of it. You have to have the engine to do it, but it's always about the pre-processing of the data that matters the most. And so it just says that don't expect this thing to fix some problem in your data. Okay, it's going to use that problem in the data to mess you up, is my experience. But I thought that was a very interesting point Taralba made. It was just saying, like, yeah. So I'm not sure if younger people can do that when they're, writing these papers for these machine learning conferences, because, they have to have a success story, and it's a lot of financial incentive to make sure they get it. I mean, somebody in, computer science that writes a paper, a few papers at NIPS, and potentially gets hired by Google, they're going to make more money than they'll ever make. Okay, so there's a lot of financial incentive to have that success happen. And I think, you have to appreciate that about some of the papers that you read. So this is something that happened, and I don't know if the physics community, you guys know about adversarial examples, but I thought I would talk to you about them because they are a product of the failure of the geometry of the neural network. Okay, and that's why I'm telling you. So this is like the usually they have these huge, the titles of the papers in the community in machine learning, they always have an acronym of something, and that for you to sell their algorithm to you. But this is the most understated title ever. Okay, intriguing properties of neural networks. You'd almost think, how in the hell did you get this published? That's such a weird title, but it was a very famous paper, and I like to think of it like intriguing properties of neural networks, right? That's like intriguing properties of airliners that they crash and blow up. That's intriguing, isn't it? We should think about this crashing and blowing up stuff if we have time, And the idea here is that these adversarial examples to the human eye look ridiculous, right? They look like white noise, and you're saying it's various objects, or at least these look like patterns. This is like how CNNs see the world. A CNN, is a filter, and it really is like a texture filter, just a baseline CNN. And so you can kind of say, yeah, maybe these things look like the textures of the objects labeled here. And then you go over into the MNIST kind of world, and you say, well, these are the numbers, 0 to 9, and you're just like, what the hell is going on, right? Why does the system think these are the numbers 0 through 9 with very high confidence? It's not just guessing, it's saying we really believe this. This is absolutely, see, that's a 6 right there, and the system is like, yep, absolutely. And whatever these are, I don't know how those got turned. This looks like Fourier transforms gone mad in 2D. So you're kind of like, this was the moment everyone was like stood around and kind of said, what are these things doing? This is very confusing. And so here's sort of a way for you to think about what's happening. So data does, because of the constraints of the generative nature of the world, like there's not that many parameters I need to make most objects or data or things. But the space of the sensor, the measurement is an enormous space, okay? Because the sensor should be able to see many, many, many different things that you will never see. That makes a good sensor, right? So a sensor picks out a very tiny wispy aspect of the universe, but it could have seen all sorts of crazy stuff, right? And that's why you like it. It's like, wow, that really picks something out very well. And so this data manifolds are actually sort of like constraints in a system. You could think of it as like, well, this is your governing equations of motion, or PDE, as looked at as like differential forms to form a geometry. And they're sitting there in that space. And it's extremely low dimensional compared to the dimensionality of the sensor space. So it's the most, the space of natural images, space all the images you could possibly have, is fleetingly tiny inside this astronomically large space that you're in. So natural images live on this tiny little manifold hiding in there somewhere. So now you show up with your neural network and you need to find, ostensibly, you want to find the geometry of this object here, right? Well, let's think about the tool you brought to play with, okay? So the tool that you are going to solve this problem with is to pick one of these functions here. Used to be in the old days, these were the functions you would pick, but now you do reloads or leaky reloads, where you don't bother with all this stuff here. You don't care about the non-differentiable nature at 0 anymore. It's like, it's all about speed, and reloads and leaky reloads have speed for their advantage. And you never pick this one anymore, which is the radial basis function in that direction. That is like, I don't know anyone does that anymore. And so, but this is an exception to some of the things I'm about to say. And so that's why that's there. So now think of this object. I'm going into my data set, and what I have is basically a funny kind of hyperplane. And I have to go in and bracket this object here with these hyperplanes, right? And sort of pack them in around it to try to sort of confine it and say, yeah, the result of my neural network is the combination of all this sort of restricting around this object to make sure I can tell the difference of these things on this manifold. Okay, so you kind of have the geometric picture. So it's kind of as if I had that object and I'm sort of putting these planes to try to put around it to say, yeah, this is where that object is in the space. All right. Now, there's a funny property to this, though. The planes will have these very high dimensional corners in them. And these corners, where the plane sits is determined by the data, right? But the data doesn't determine it enough to make sure the plane is in the most ideal geometric way compared to the manifold. All it has to do is get the labels right, the supervised learning right, your cost function right. And at some point it says, this is good enough. There's no way to change it. So we're done. We can stop. Unfortunately, what happens is that you can have these corners in these spaces about all these planes trying to bracket this thing. And I don't know if you've ever worked that problem where you take a hyperball and you put it in a hypercube and you ask how much of the volume of the ball is there compared to the volume of the cube itself. And as you increase the dimensionality, you discover that there's nothing in the ball. all the space is tucked up into the corners of the high dimensional space. Okay, so all this high dimensional space is like hiding up in here, up in these corners, so to speak. Now, and here's the other interesting thing is you've never seen any data there. Okay, the data was down, just pinning the planes down in some other place, but since the plane extends on forever in the space and other planes extend and other planes extend, you can form these corners and they can be up above where your data is, not where the data ever was. And there was no real reason why would you think that there would be this way of sitting up in this corner. The data never said it. It's an artifact that you use these planes to kind of build up your solution. Okay. And so if you think of these adversarial examples, they are kind of the artifact of this sort of phenomena. where lazy neural network stops, let's say here. I'm trying to split these two, like these are two categories, like 3 and 8 or something, right? And so the here might sit like that. Well, what I would have really have liked is to have the normal of my hyperplane sit in the or tangent vector, like this. This would probably be a better solution, and it's kind of what you think it would probably do. But this turns out is what happens more often. And so now you have this sort of funny geometry where you can say, here's some real data. And now it's very easy to actually trick the system by very tiny nudges across these boundaries, because this big has not been lined up well in the high dimensional space. It's doing a good job on your training. Okay, your training is fine, and even it's really it's generalizable too. Okay, so everything looks fine. It's just there's this weird effect where you can add this. This looks like, oh, that's just some random noise, right? That's not random noise right there. You actually had to be learned by a network to be able to understand where you push to do this. This is actually a way of thinking about a very high dimensional normal vector. And so this is a high dimensional normal vector to this place on the manifold. And you add, look, it's a small thing. So like if I show you these images, it really registers nothing. You know, it's like there's nothing, you didn't do anything to the image at all. It's like that image there looks like that image there. There's no difference. But this tiny little push through this boundary right here completely changes the outcome. Okay, and it's because you've not really regularized this correctly. You're not orienting this boundary robustly. It's not robust to these small perturbations. And so that's what led to this whole problem with adversarial examples, where you can, people can put a little sticker thing on a stop sign and change what category it is for an automated driving system. And you can imagine all the havoc that can come from something like this. And so this kind of concern about the regularization and getting this right, you might say, well, okay, so this was years ago. They fixed this, right? Sort of. Let's talk about the fix. So the fix was the GAN, right? And so this is the classic bug as feature. And so the GAN is trying to say, well, all right, so this happened. So why don't we try to play a game here and pretend in some way we can compete two networks against each other. And the network is, one of the networks is the original network you might have been trying to use, that makes this data. But there's another one that says, well, I'm going to take random noise and I'm going to try to learn to trick you in a discriminator to create synthetic data that's fake data. And then this way, these two kind of go into some sort of game theoretic optimization problem. And then the trainer, the thing that's creating the generative model here, creating the data, and this is trying to create data too. You actually sort of create an interesting generative model. And you might ask, well, what is this thing doing? Well, it's trying to correct the fact that you shouldn't have data that's outside of that manifold structure and be able to say, yeah, I saw no data there, but I still believe that it's some object that I know. This system is preventing that. It's like it's sort of saying, no, if I generate the data, it's going to have to be either near the manifold, so we're going to bracket that manifold more closely, or else you'll be able to tell it's fake. All right. And so when the two systems converge and when this output basically comes like a 50-50, it's like, well, you're done. It's like, well, it's perfect. It's randomly guessing whether or not it's fake or not. So that's kind of the idea of what the GAN does. But geometrically, it's like trying to fix this weird problem of having these planes of the neural net not really be aligned correctly compared to the data in that manifold. And so to me, it's good to have a geometric sense of what's going on, but it's also a warning about use non-local support in your functions. See, that's the real problem was in some way. Fighting and fighting is this. It's intermittent. I don't. Oh, I see. Okay. Okay, I think it's okay now. And so I lost my train of thought on that. But in any case, it's this dot, a non-local support. It's like the fact that you use something that was like a hyperplane, and in fact, not something that's a little bit more like this object. Okay, this is like more of local support. And in fact, in this very paper, the Goodfellow paper with the first adversary examples, they made that comment. They said, for some reason, when you use these radial basis functions, this doesn't really happen. and it was just sort of like, who knows? I don't know. It's just an interesting comment when we tested. But like a lot of computer scientists, they said, well, but of course it's slow, so we can't do it. It's too slow, right? It's almost like the accuracy is not as important as the speed for that. And so that was just like they moved on. And it's like you could go in and create local support and not need a GAN, or you can say, no, I'm gonna stick with my relo, my thing to be slow, but now I have to train a GAN. It's a very strange way to think from my standpoint. So I know, I know some people are using here. I saw it in some of the talks, and they can. It's interesting, but I would encourage, if you're using GANs, to sort of think very deeply about what that is. What you're using it for, and the alternatives to using a GAN. So probably enough said on that. All right, I'm not sure I want to pick on the machine learning people anymore, but it's important for you to know how they develop their algorithms. Is that, usually you as a scientist hold your data fixed and you try different things on it. They do the opposite. They're actually saying, they're going to standardize their data in a sense, and then the algorithms come through, and it's almost like a game now. When you look up on a paper, you look at the paper in machine learning, you flip to the part where they have the bold-faced numbers, like they're against everybody, and then they wrote the paper because their numbers are bold-faced and the other guys aren't, right? And then you go, oh, look, he's got the best algorithm this week. And then they compete for that, even though you're like, aren't we way down in like the Bayes risk noise of this? I mean, are we actually able to claim that there's any difference anymore between some of these algorithms? But it's a competition. People need jobs, people need tenure. And so you have to be aware that this is a structure about how they build these algorithms. Now you can pull things out of this and try them, that's good, but you have to be aware of that they've been tested on this, whatever this is, the standardized data sets that they use, all right? And the problem is you have to realize there is no model in machine learning of the intrinsic complexity of these problems, all right? They just have to try them and see how hard they are, okay? So if you had a model of intrinsic complexity of a problem, you wouldn't really need to have standardized data sets. You'd know how hard the problem is in some way. All right, I think I've beaten up on neural networks enough. I'll just add that it's like this is something people say, and it just drives me crazy. Is that, well, neural networks are like your brain? Well, they're not. Mathematically purified neural networks that are using machine learning are not really very much like what's in your brain. All right, the cognitive scientists go berserk when machine learning people say this. But the problem with neural networks is they sort of have this, like you pin a machine learning person in the corner about a neural network, and they say, but it's like this neuromorphic computing or something, it's like the brain. And it's like, yeah, I know the brain is an existence proof that something like a neural network can do something. That's great. I have a brain, you have a brain, pretty good hardware. But it's not clear that we want to, just like with airplanes, say, well, the goal is to emulate that and create something where we flap our wings. And that's how the object should be. That's the neural network. It's like, no, I think we have to create something like the propeller, something like a statistical object here that actually isn't dependent upon this inspiration like a neural network, and it has some statistical properties we can. So it's kind of like in this pairing here, it's like flapping wings to firing neurons, propeller equals what? What is the algorithm that we would really like there, the structure of this? And that was something I'd say physicists actually can make a great contribution to. You know, physicists, physicists just think, I'm going to have to, like somebody in one of the talks said, you have to choose. You're going to be problem, or you're going to do the machine learning side of the problem, and you have to choose and be happy. I am the person that says, no, do not choose. You will do better and to learn the machine learning from the physics than just handing your enterprise off to the computer scientist person only focusing on the machine learning. Okay, that is a recipe for disaster. All right, you have to own your problem and understand how to carefully bring the machine learning into it. It can't be separated like that's just, you know, ironclad technology. It's machine learning is not like, you know, LaTePak or BLAS or numerical linear algebra packages. People build airplanes with those, and our families fly on them, and people don't die. Okay, now that's software. That's good stuff. This is not there yet. So you have to be a lot more careful when you're using kinds of tools. So the time has gone by rather quickly. All right. So as I sort of finished up a good portion of the talk, it's sort of thinking about this geometry is where I encourage you to come into the problem, because I think geometry provides good insights, and from physicists, it's something where your intuition about geometry has served you well. And so you have to realize the underlying assumptions of machine learning are that you are in some giant RD vector space. Okay, so they believe that all the data is in a giant vector space. Mind you, it's also smooth differential because you want to use gradient descent. Okay, that's can be a significant assumption. And because they take linear algebra and undergraduate multivariable calculus, that these are the tools that should be amenable, that this is like a global chart on the whole space, and we should just be able to use linear algebra and freshman calculus basically, and be able to do whatever we want. That's kind of the mathematical set a lot of times for machine learning. Now, do you believe this? Do you believe your data is a vector? A vector, I mean, a vector is a pretty special object, right? Remember a vector, it's like you can add two together and you can make 0. It has a scalar multiplication. I mean, who knows what your data, what if your data is spectroscopic and it's positive definite only? That's a vector? I mean, you have to think very carefully about what space your data is in, because the assumption of your machine learning algorithm is it's in this space and it's going to treat it that way. And so you have to be aware that that's going to happen. So the way to look at it for me, and this is sort of getting into the more technical way of looking at it, is as these mappings. You say, I have a data set, and yes, I believe you can concatenate your data. And then just a data structure that's and it's sitting. That doesn't mean it's. Yes, it's like a vector, and I know we represent that way in linear algebra, but that doesn't mean it obeys the properties of a vector. And so that manifold I was mentioning, that's probably hiding out there in this vector space, and that can be trouble for you, right? Because actually, this manifold is your friend because it's the last place you probably can do calculus. Right? It's the most general object where the property calculus and the limit force will work on spaces. And this object is your friend, and you should find it. You should not. Somehow the neural network, the machine learning is kind of doing some crazy way of trying to get at this object right here. But I would argue maybe you go more directly at it. Okay, you look for it more directly. And so you're saying, yeah, maybe I have a global chart. In the embedding theorem, we can always take any manifold thing and double the space. Basically can stuff that into a global chart, right? From the embedding theorem, from geometry. And so we could say, yeah, okay, so maybe we'll let them have this giant space, but we really know we need to find this sort of non-linear structure that's hiding inside of it. And as physicists, we like symmetry, right? Symmetry. It's very useful to be able to do like a coset of something and say, hey, I'm going to take this big space and mod it out with a Lie group, right? And say, it's kind of like I'm looking at a manifold, but I may be able to productize in a non-trivial way, like a fiber bundle. I can actually say, yeah, this is like a principal fiber bundle now. I have symmetries connecting to a manifold, and I can understand that there are directions where I can move that don't change my label. And now this is becoming a lot more powerful to think this way. Another important idea is that distance, right? Every machine learning algorithm is implicitly saying there's some distance measure. Like I have a data point, I have a data point. Are they close? Are they far away? Right? That's what it's using to solve the problem. So you need to think about, well, aren't we kind of expanding minus log p of similarity between two data points? And we're sort of picking off that first non-zero term, this leading order term of something distance squared on this manifold right here. Now, we don't know manifold to start with. This is the problem. We may be trying to learn manifold from point cloud data. So what we do, and this is what happens, this is what goes on in machine learning, okay, too. You pretend it's Euclidean. You say, well, I don't know this distance function on my manifold. That's like the geodesic distance, this guy right here. I don't know that. I can't compute that, from my point cloud data. But I can claim that this is true, that this Euclidean distance metric is available. This is every time I'm in a project, there's this happens very early in the project where someone says, is this enough data to do? Know whether it is or not. But this is the trick. This is how you understand how much data you need. Because where this is true somewhere. Right? You have to have the data packed together. It's like saying geometrically, I have to have enough data to detect the tangent spaces. Because on the tangent spaces of that manifold, this can be true. But if I don't have enough data to be able to detect tangent spaces, and it's just a ball like curvatures and things, and I can't really see what's going on in the tangent space structure, I can't claim I'm doing this. This is the key. So you have to have enough data in the right places to make that true. So it's a global question. A lot of people say, well, I have 1 trillion data points. I don't care. It's irrelevant. Big data is a joke, right? It's the right data in the right places that you need. And the right places are to have enough data where there's curvature. You need enough data where there's curvature so that this is true. Then your algorithm will probably work, okay? If it's not true, I have no idea what will happen. Maybe those spaces aren't that important to you. So this is just saying what I just said right there. So this figuring out what is close statistically and far statistically is the key. Yes, sir.
I have a question, like, because I mean, I'm totally with you, and like I follow the fact that very likely your data will lie on a lower dimensional manifold than the space they are embedded in. But what you're doing there is like, as far as if I'm understanding correctly, like you are inheriting the metric of the space you are embedded in and saying this is the space of the manifold. And you're saying that this is something that it's not necessarily true. But what I would say is that if the manifold is lower dimensional, then that if the dimension of the manifold is very, very low, then like this is never the right thing to do. You're always prone to the adversarial attack thing, because right, this notion of distance is always wrong in a sense.
Well, no, I'm saying this notion of distance can be right. This is the distance measure just in the ambient space. You agree? We're embedding in flat space. So now we go and do an injected map, then we stick our manifold in there. Trouble is we don't get to see the differentiable structure of the manifold. We just get, let's say, points, right? So points are not even topology. They're just some points sitting there. And for those points, we have to infer this structure. Say, well, how will we induce a top cloud? And what I'm saying is, well, the way to induce it is if I'm going to be true to your data, I claim I should do embedding. Okay. Now, why somebody says no matter, but I would say that you collected the data in some way that mattered to you from the instrument, and when you the algorithm, me on the algorithm designer side say, well, if I'm going to hunt for a manifold, I have to respect the metric of your space you collected your data in, which I claim this across the whole space. All right, I know your eyes are getting wide, like, oh my God, what's happened? We're in trouble. I claim it's not trouble, it's flat space. This is true in the high RD space, it's flat. There's no problem with that. And what I'm saying is we inherit the metric from the space we're embedding in, right? That's an isometric embedding, right? So we are going to use that metric, bring it onto our manifold. So what does that mean? An isometric embedding is nothing but the projection of your subspaces. That's all it is. So you're just projecting it down onto the lower dimensional tangent spaces. The trick is you better have enough points in the right places that you can identify those tangent spaces, because that's where you will know how to do the projection and have the low dimensional version of this, right? Okay, now did that help any, or you're still like,
Yeah, it has helped.
okay.
That you are saying to me that you are referring to the tangent space, or you're saying that you are so you are estimating the gradient in the tangent space, and this is something that you are forced to do because of the way the algorithm works. You evaluate the gradient on the data points.
Yes,
So,
exactly.
And then you're saying the metric at least has to be somehow at least the right one in this place here.
Yeah, so just
that's the point, right?
Yeah, exactly. I'll have I think the next slide has a figure to speak to.
I'm getting it. Okay, thank you.
Oh, I should have just put this up. So so I'm saying that when I have that Euclidean space, it's only good here, but it's not the same projection, of course, if I'm over here on this tangent space. It's different. Yes, the metric looks the same because that's, it's like I haven't done anything subspace over here than I have over here. So metric tensor will be a function of position in the space. That is kind of what defines the embedding into the space. So here's my point cloud, and we can see that, well, if I have enough points, and I can say, yeah, I think I did tangent space. Now that's a question. Now that's like on our to-do list as a task. I haven't said I've told you. Okay, but I said we know we should want to do it, right? We want to do it because that distance measure that we need for statistical similarity, it only works there, right? So I better go out and realize that to have the right space to be in, I need to find these things, and I need to be able to live in this very tricky regime. And this is why you don't have this tool on your laptop right now. Okay, this is the trick here. It's a finite sampling problem. The finite problem is that you need to live in a very careful regime between two extremes here. And these extremes will mess you up. right? The first one is you could have just this high dimensional noise ball. In other words, like I'm here and I'm looking and I'm looking and I'm looking for the embedding space, but all I see is if I'm looking at a point cloud like this, I'm going to think I'm in, if I have n points inside a local region, I'll think it's n minus full D of the big space because I only have so many points. But if I look at them, looking over range, I have to detect this tangent space before my region, like my ball here, grows so big that it's starting to see the possible curvature. So there's the noise, the finite sampling noise to detect the dimension of your tangent space. But then there's like, if you make your look too big, you're averaging over the curvature of the manifold, and that's bad. We know you're not. You're actually, not measuring it on the surface of the earth, but cutting a tunnel through. Crazy. Not measuring the distance you want anymore. So it's this subtle trick of being able to detect a tangent space in a very high dimensional space with a very small number of samples. That turns out to be the linchpin of doing the right function, that you have this Euclidean embedding of your in the space. Okay, so that, are there any, this is like the key point about what you should want in an algorithm and how you live up to the assumptions that are in machine learning about the Euclidean space and actually make it work. Oh yeah. I apologize, sorry.
No worry. So your argument is that when you're addressing a task, your task is represented by your data being in a manifold, and then you're looking to this manifold through the embedding in a vector space. Fine. But then you're saying, you're asking the question, are my data enough? And the answer is related to, am I able to resolve features of my space, my manifold inside this vector space?
Yes, exactly.
But then I'm not sure that my task is just a manifold, because in some sense I have to provide a function on this manifold. So if my low dimensional space has some features that are not very sensitive, so there are tiny features or something that is not changing the value of the function, I don't care so much about this feature of my latent space of my manifold. So at the end, my data are enough if I can resolve variations of my function on this space. If my space just partition the manifold in two, so I don't care so much about resolving it or
okay. I think I understand what you're asking. So imagine it mathematically. I'm saying I want to learn a function, right? But so it's regression, and it may be regression where I look for boundaries, like it's a classification problem. Are you comfortable if I said, yeah, in the x's, and y equals f of x, the x's, I'm not going to tell you the space they're in.
Sorry, say it again.
The space that I start in. If I'm building a function, y equals f of x, and I don't tell you the space that x is an element of Rd, okay, it's not. It's an element. Yeah, the support of the function. So oh, well, let me come to that.
No. The idea is that think about, you have a very complex space like a tree or something like that. Okay. So you have many branches and so on. But then in the end, your task is just partitioning your tree in half. And then maybe I will find an hyperplane in my vector space that is partitioning the space in two, but it's also partitioning the tree. I don't need to resolve the full tree, because the moment I can partition the tree in two parts, it's just partitioning the function.
So this is, I think I understand your point. It's actually in machine learning and from statistical learning theory, there's this thing called Vapnik's maxim. And Vladimir Vapnik said, don't solve a harder problem on the way to solving an easier one. right? And so he was like, well, you need to solve it for the labels. You don't need to find the probability distribution function that generates the data if all I have to do is tell the difference between the cat and dog pictures.
Yeah, something like that.
Right? And I would say, well, I appreciate that. No one wants to do a lot of extra work, but this is sort of a slippery slope, because this way I was talking about supervised learning is a very tricky beast. It's like there's penalties to be paid by the shortcut. To not understand where your data is geometrically, how it sits in the space, and say, I'm betting everything on this regression function, right, is risky, because the algorithms will take incredible shortcuts to find the answer to that problem, and they may send you down a very dangerous road. So I would just say you have to think extremely carefully about making your problem easier. Whereas if you really are concerned about the nature of your problem, I think you have to say, I would really like to have a little bit more of a better sense of the generative structure of that data. I want to know the support of that function a little bit better, especially if I'm hunting for things in high dimensional spaces like this.
Yeah, I can see your point, but the practical point that I'm putting out is that sometimes my data might be enough to solve my task, but not enough to solve.
Yeah.
So I don't know if I'm stable too, but if I just reduce to the
I agree with you. This comes down to this: how much data do you need? And what I want you to never ever care about is N, global N, for the total number of samples for my problem is large. I don't care. It's irrelevant. And kind of for the reasons we're talking about right here. I want to know where that data sits in that space. Now, I look at it like this way. You're doing it your way. You won't be able to see this structure, but you're saying, maybe I don't need to. And so we go and we look at this and we say, do I have enough data to find the structure here? If I don't have enough data, I'll never figure out where these tangent spaces are. I'll never understand the underlying support of your function. But if you say, well, okay, maybe, but I don't care about my function out here. I don't care about my function out here. I just care right here because this is a class boundary, let's say, between two things. And that's all I care about. So it's almost like you take a mask and put it on top of the whole thing and say, to know the manifold everywhere, but I might need to know right in here where I want to know it. And if I have enough data there, I can solve my problem, because I'm not trying to find the manifold everywhere, but I might need to know it around the boundary. Is that fair?
I can prove that I'm solving my problem, but effectively I'm doing it. Even if I cannot tell that, yes, that's the final answer.
And that is why supervised learning can work. But sometimes it doesn't work right. And you have to wonder, well, the underlying geometry is creating a problem. That's not, in other words, you're not where you think you are in the space where that boundary is, and you're not able to construct it. So yes, the shortcut works, and a lot of times it can be okay. But for a physics problem, I don't know. It makes me nervous. If you're doing a physics problem, I sort of imagine the world isn't as friendly, that something bad could happen. And I'd rather just try to know this.
Yes,
right?
Definitely. So you don't only want something that is working, but you also want to know why.
Yeah, I want to know why. And I want to know when more data comes in and it stops working, what happened. I want to know geometrically, the new data came in, the answers are different. And I want to say, look at that. You created an aneurysm between the tangent plane structures, and I lost an understanding of the dimensionality of the manifold. And if I said that to you, I think as physicists, you'd go, wow, okay, can you show me that's true? And you'd say, that's a good explanation. That's explainability, that's interpretability, and that's what you should want. If I tell you that, I don't know what to say, if the neural network worked, stopped working, isn't, it was great and it's not, I don't know what to say. It's like hard to figure out. You do, ablation studies. You know what an ablation study is? It's something where computer scientists learned a lesson from biologists, where biologists didn't understand like how something complicated like a cell works, or a genetic regulatory network. And they said, well, we're just going to systematically break pieces of it and run it and see what the effect is. That's an ablation study. I'm not sure you want to use that to understand your physics problem. I mean, if you wanted to, you should have become a biologist. All right, so I am kind of inclined to not launch into something else here because we're sort of near lunch. So maybe you've had enough. Okay. But maybe if you just give me a few more moments, maybe I can show you some things that if you're interested, we can talk about it offline. Okay. And so I'm going to be kind of quick, and I'm not going to expect it's like, okay, I'm not going to teach you, help you understand it so much as just say, well, if you like this, there are things to do. Because right now, look at what I've done. I've just written you a giant, promissory note, sort of like, yeah, we should go out over here and do something. But I haven't really told you like, well, what? Tangibly, tell me what to do. What will we do? And that's the part, is sort of the next part. One of these things is, well, this is a little more technical about using experimental calibration and things. In other words, let me quickly say this, because there may be people who don't use their calibration data. They don't know, like, where does your calibration data go into your machine learning algorithm? They never heard of calibration. Computer scientists don't know what calibration is. So the problem is that when you have calibration data, that alters the statistical similarity structure of your space. And so even though I may see these little clouds here, these turquoise points, they're all the same. That's a copy of the same data 3 times. But it's not really the same data, because look at the covariance structure behind it. That covariance structure is your calibration. That's when you said, well, if I put a reference standard into my experiment and I look at the spread on a fixed point, it falls inside this region of this Gaussian out to 1 sigma or something. And then I go over here and I say, well, whoa, it's not homogeneous and isotropic. This is kind of what you'd like your calibration to be, right? Sort of uniform. But let's say your calibration is different, like off into the edges. It has orientations. There's covariance structure to your calibration. And you say, yeah, when I do my calibration, I have this field of ellipses that looks like this. It's inhomogeneous and anisotropic. This changes the space. This changes the structure of it, because there's a nice little rule, which is that the metric tensor for your calibration is the inverse of your covariance of your calibration. And so what you're doing is saying, I have a 1-1 tensor field, fancy name for a linear endomorphism across the space. And so this tensor field actually makes the locations of the data different. In these cases, you may say they're the same data. It's like, no, they're not. They're sitting on different spaces, and you have to incorporate your calibration into that metric tensor. In other words, the space we're embedding in is no longer just Euclidean, right? That was our assumption we were talking about, saying, I'm just using y minus y magnitude squared. This is saying, no, your calibration measured the fact that the data is embedded in a not flat space. So use the information. It's already on a manifold, and you measured it by doing your calibration. Okay. So I thought that was the point. And it's not like it's some massively tricky thing. It's just sort of understanding that, you're sort of understanding how to do this mapping to turn this space into that by just finding the Jacobian. It's like the Cholesky decomposition of the inverse covariance. It's not some miracle being. But if you don't do this, you're leaving information on the table you should have used in analyzing your experiment. And just because the machine learning contraption doesn't have a slot for your calibration data, don't think there's not a way to do it. There is it's a problem. All right, so I will do what I promised. So this is sort of like getting into this fiber bundle idea and thinking about, well, what happens if there are directions in this manifold that don't matter? Okay, and those are like the fibers. There's like the fiber base space, and here's the fiber, and it says you can move up and down this fiber, but it doesn't change your label or your regression. So this is a symmetry. It's very much like I modded out with, like, let's say a Lie group or something. And, you know, this is very much like here's space-time, and we tacked on, you know, SU3, SU2 at U1. And we said, well, that's a gauge symmetry. You can set that however you want, wherever you want. And the connection that makes sure you can do that, we'll call the bosons. And so this way of looking at like a computer vision problem, it can be very powerful because it allows you to understand what parts of the spaces are your symmetries and what part of the spaces do your classifications and the things that matter to you. So I don't know, I'm really, the theme here is care about the geometry of your problem, and it can pay off handsomely. And it can be more like physicists doing machine learning and not physicists inheriting the computer scientist version of machine learning. All right, so I'm not going to go through this example. I said I would talk about this. I don't have time to talk about it, but those that are interested, whenever I come to a workshop, I like to have something that I do for work because it's a workshop. So I was watching you guys do this stuff with hypothesis testing and anomaly detection for high energy. You're using neural networks and things like that. And I thought, well, you know, I should be able to take what I'm telling you to that problem, create maybe better. It would be, but it's like, it would be fun to think one could do that. You know, if what I'm saying has real merit, right, it should be better in some sense. And so I started building a version of this style of algorithm for doing this kind of anomaly problem. And, you know, this is like just something over, you know, a weekend, but it's interesting how it does things that I don't think easily get done by the neural network. So if people are interested in chatting about that, just to say, what is that like? You know, what happens with that kind of data? This is actually, Gaia gave a great talk, Gaia Grossa, who she's at Padua too, working with Marco Zanetti. I stole her slide here. I kind of learned the problem by watching their talks last week, you know, and this is someone else's slide I thought was pretty good, explaining the likelihood ratio trick for doing this anomaly detection and turning into a supervised learning problem. But, you know, what I have sort of done, and I'd love to talk to people about it and see what you think of it, is that say, well, let's go back and do this local support version of that problem, not the neural network, but we go in and we say, yeah, we have some crazy point cloud generated from the synthetic data, the Monte Carlo data of the standard model. And then we want to analyze it and try to find those tangent spaces and try to find that structure. And so you grow the ball and you start doing kind of a detection problem there. And now remember, in that problem, as I understand it, then you have some anomalous data, right? You manufactured it somehow, or it's real data even, maybe it's real data. And you say, well, can I tell the standard model data from the other kind of data and be able to tell you how different they are? And just to give you a sense of what would be fun to talk about is I turned it into a coin tossing problem and just said, oh, well, if you formulate this problem in the right way and just ask, I put a ball around something and I just ask one question, is there any data point I draw from the Monte Carlo in the ball or not? That's the only question I want to answer. And then what you do is you just expand the ball. This is a arguably trivial Bayesian inference problem, right? You just easily solve this problem. And then you say, but I don't know the scale to be at, right? So I take the ball and I just grow it and I solve the Bayesian inference problem at every single scale. It's trivial to do because it's all analytic. And what I'm really finding is that as I grow the ball, I watch that between the two data sets, here's the ball where the data is. This is the global, the total data set. This is from some data that Gaia provided, just as an example here for me. And then you look at the number of things in the ball. So it's kind of, these are the coin tosses. It's just saying, well, how many coin tosses at this size? How many go heads or tails at this size, and this size, and this size? And you're looking at the two different data sets here, the black and the blue curves, and you're sort of comparing them and saying, well, that's a density, that's a over density or an under density, the gap here. But the trick is you can't say that, because what I'm doing is I'm doing Bayesian inference of the probability of being in the ball. actually have control of the finite. It can be vastly different total number, and it doesn't matter here. It can deal with all the finite sampling issues. It has no between these two curves. You guys like the well, this is the math of doing it, where you're sort of like saying, okay, well, let me write down the probabilistic graphical model. The standard model is saying that both data sets are made by the same coin, right? So I'm tossing one coin, but I'm separating the data sets to fool you, but there really is just one coin to doing the toss. The new physics kind of model would say, there's actually two coins. One coin, for the standard model, but this other data you gave me seems to be coming from a slightly different coin with a different bias that you're tossing. And the question is, in model comparison between the two, can I tell the difference between this scenario where it's advantageous two coins, one coin, and this is the solution. I mean, it's not really, from a Bayesian standpoint, this is actually fairly trivial kind of computation. And now you say, it's just a bunch of beta functions. And then I know you love the likelihood ratio and like Neiman-Pearson and all that good stuff. So it's like, sure, I'll form the Neiman-Pearson ratio. It's a different one than you guys seem to want to calculate. It's local. It's a local one. It sits in the data set, finite sampling a ball, and then asks, what is that ratio? It's not the global value. Flashlight. Shine it around. You can ask the question whether or not this log ratio test here, this is the thing you like. This is like Neiman-Pearson. It's just on a subset of the data. And it's just this log of the beta functions of these arguments for, well, how many counts did you see in the ball for the A process and the B process? So it's pretty simple. But it has a lot of power in that it's fully controlled via Bayesian model comparison and has good finite sampling properties. It doesn't care if big NB and big NA, the total amount of data in either set are very different. It's irrelevant. And so you end up doing, when you compute this, like on like a one spot here, like here's a little ball. The kind of things you see, so it's kind of like this likelihood ratio sort of spikes and falls down, and you might say, well, there's some, I hate to say it, there's some p-value that you want to go to, like up here, and you say, if this thing rises above this p-value, this is the 50-50 line, right, for log likelihood. If you can rise above that value, you say, there's evidence that this is due. Right, if this value spikes very high. But the thing is, it has full interpretability, because it's built in, because I can, well, that's just in this one place. It's right here. You say, new physics isn't. It's like it's right here in the data, and the ball has to be this big to detect it. So it's a pretty clean explanation of why data was anomalous. There's ways to do the global likelihood and probably get back to where in the data it was doing that. But this is it's kind of a trivial a way to do it. Support idea that I've been sort of selling to you. We have this phrase in America, eat your own dog food. Well, your own dog food means if I'm telling you to do something, I better show you I will do it. Right? And I'm like, I believe that local support on this kind of chat about it would be fun.
For sure. Now, one quick comment is that, first of all, our anomalies may not be entirely due to some local. So they're not necessarily somewhere such that there should be a peak.
Yeah, this is
all of it.
This is not a bump.
And the second thing is that Bayesian or whatever, at some point you need to do some sort of coverage test. And if you are looking in several places, you will have to tell me how confident you are that by chance you didn't find a peak, right?
Yeah, that's the p-value. So you have to say,
you say it's local.
Yeah, but it's local.
But you have many local places where you can look for.
Yeah, but if you find any one place, it's significant. So the significance test is being applied locally, scanned around your data, as opposed to saying there's a global version of it. But this is not bump finding. This is saying can find slight changes in density. It's not a peak. There's no assumption of a peak.
No, this I see. But Okay, we can discuss.
So we
later.
can talk
But
about,
it's-
but actually I
So
want,
it's a good thing being global, if you really want to tell whether it's weird or not, your entire data set, no? Not a bad thing.
well, but yeah, this is fascinating. We should talk about it because
Yeah, we will do.
we will
But
talk.
now let's,
Yeah. So sorry, I
send
didn't
people
really,
to
I kept you,
no, this is
Longer.
time for one question
okay.
to
So,
conclude. those.
so anyway, if anyone wants to talk about these things, and actually the slides that come after this are sort of getting into the explanation, but how? So I've led you right up to the precipice, you know, and I want you to jump, but now it's like, okay, I can show you how do you do this? How do you sample? And it's very interesting. It's an interplay of differential geometry and random matrix theory to be able to figure out how to do these samplings and find these tangent spaces. So there's a rich mathematical structure that I think physicists would be like, yes, exactly. We use random matrix theory problems. Through it, and it's fun. So thank you very much. Appreciate your attention.
Thank you very much. Maybe there could be time for one last question. If people want, or if people prefer to have lunch and discuss for with more relaxed time.
So I'm around for the next 3 weeks. So I'm here. There's plenty of time to chat if you want to. So
Very good. Okay. So thank you very much again.